Hello student, in today's class we will describe about isomerism in coordination complexes. You have already read about isomerism in organic chemistry. Here we will discuss isomerism in coordination complexes. Generally, coordination complexes having tendency to show two different types of isomerism, one of which is structural isomerism and the other one is stereoisomerism. Structural isomerism are those having the same molecular formula but the structural arrangement of the ligands will be different, and stereoisomerism occurs due to different spatial arrangement of the atom or group around the central metal atom or ion. In both the cases, structural isomerism and in stereoisomerism, there will be no change in the coordination number. Structural isomerism further classified into the following part. First one is ionization isomerism, second one is hydrate isomerism, third one is linkage isomerism, fourth one coordination isomerism, and the last one coordination position isomerism. And stereoisomerism are classified further into two categories, geometrical isomerism and optical isomerism. In this class, at first we will describe all the different types of structural isomerism, and thereafter in next class we will discuss about stereoisomerism in detail. Let's start with the first one, that is ionization isomerism. The definition of ionization isomerism is that the coordination complexes have the same molecular formula but produces different ions in the aqueous solution are known as ionization isomer, and the property is known as ionization isomerism. Let's start with an example. CONH3 whole 4 Br2 and Cl2. So this part is known as coordination sphere and this part is known as ionization sphere. If it get dissociate into water, then it will release CONH3 whole 4 Br2 plus 2 plus 2 Cl minus, which means it releases the chloride ion. This can be changes in this pattern, CONH3 whole 4, chlorine present in the ionization sphere migrated to the coordination sphere like this, and Br2 migrates into the ionization sphere. So when it gets dissociated, it releases CONH3 whole 4 Cl2 2 plus 2 Br minus, which means these two have the same molecular formula but producing different ions. In the first case producing 2 Cl minus ion, and in the second case producing 2 Br minus ion. So these two complexes known as ionization isomer, and the process is known as ionization isomerism. Here you can see that the coordination number 4 plus 2 6, and in the second one again coordination number 4 plus 2 6. So there is no change in the coordination number during ionization isomers. Now let's move on to the next topic, and that is hydrate isomerism. It is very simple. The isomers which have different number of water molecules inside and outside of the coordination sphere are known as hydrate isomers, like COCl3 dot 6 water or CrCl3 dot 6 water. This can be written like this: CrH2O whole 6 coordination sphere, and this is Cl3. In the first case, we can see that the 6 water molecule inside the coordination sphere, and there is no water molecule outside of the coordination sphere. So, it can be further written like this: CrH2O whole 5, 1 chlorine goes into the coordination sphere, 1 water and 2 chlorine. In the second example, we can see that the number of water molecule inside and outside of the coordination sphere are different, that is 5 and 1. And the last one, CrH2O whole 4, 2 chlorine comes inside of the coordination sphere, and it is 2 molecule of water reside outside of the coordination sphere with 1 chlorine atom. So in the above example, we can see that the water molecule inside and outside of the coordination sphere are different. So these three are known as hydrate isomers. And there is a trick to find out the hydrate isomer. Suppose a particular example is given to you and water present inside of the coordination sphere and there is no water outside of the coordination sphere. When you write the hydrate isomer, what you need to do, you have to migrate the water present in the inside of the coordination sphere to the ionization sphere. Now, move on to the another topic, and that is linkage isomerism. Linkage isomerism occurs when the coordination complex attached with the ambidentate ligand, because they have rearrangeable donor site, so their linking site may get changes, and therefore such isomers are known as linkage isomer. So we can write like this: CONH3 whole 4 SCN whole twice, and outside of the coordination sphere it is Br2. Here SCN we have already mentioned, it is ambidentate ligands, donor site in this case is sulfur. So what we need to do, CONH3 whole 4 SCN whole 2 converted into NCS whole 2 and Br2. So whenever the ambidentate ligands present, what we have to do, we have to only rearrange the donor site. For example, if NO2 will be given, then we have to write ONO minus. If CN is given, CN minus, we have to write NC minus. So these are the linkage isomer, since central metal ion attached with the rearrangeable donor site of the ambidentate ligand. Now the fourth one, coordination isomerism. Coordination isomerism are those in which the ligands interchange between two coordination spheres. For example, if we write CONH3 whole 4 and PtCl4, then what will happen? Chlorine get in this side and ammonia interacts with the platinum. So we will have COCl4 and PtNH3 whole 4. So such type of isomers are known as coordination isomers, in which ligand interchange their coordination sphere. Ligand present in the ionization sphere migrate to the cationic part, and similarly the ligand present in the coordination sphere migrate to the anionic part. So these two are the example of coordination isomers, and the property is known as coordination isomerism. Now the last part is coming, that is coordination position isomerism. Such type of isomerism occurs when the bridge ligands are present, or the bridge complex is taken as an example, and such type of isomers arises due to the symmetrical and unsymmetrical arrangement of the ligand. This can be better illustrated by taking the given example like this: NH3 whole 4 CO, and the bridge ligand is OH attached with the another CO, NH3 whole 2 Cl2. So this is taken as an example. In this part, cobalt is attached with the 4 ammonia, so its coordination number 4, and in the right hand side, cobalt is attached with the 2 ammonia and 2 chlorine, the coordination number 4. These ligands are known as terminal ligands. These are terminal ligand. Here we can see that the terminal ligands are attached unsymmetrically. In the left hand side 4 ammonia present, and in the right hand side 2 ammonia and 2 chlorines are present. So what we have to do, we have to write like this: NH3 whole 3, because total number of ammonia becomes 6, and there is chlorine, cobalt, OH, CO, NH3 whole thrice Cl 2 plus. So in the above example, unsymmetrical arrangement of terminal ligand, and in the given the last one, the arrangement of ligand takes place in symmetrical way. So these two are known as, this is number A, the upper one is number A, the lower one is number B. These two are considered as coordination position isomerism. There